Welcome to, it's nice to have an in-person seminar. So I want to welcome back to Stony Brook, Kelly Lombardo, who is coming to us from Penn State University. So I want to give a little bit of background on Kelly before we get going. Kelly received her master's at University of Albany, and then joined my group and got her PhD here back in 2011. So time flies, since it seems like it wasn't too long ago. So forth, and then she stuck around for a postdoc for a couple of years. Did some climate work, actually, regional climate stuff. We had some fun with that, looking at storms that way. And then she went over to the University of Connecticut, where she was an assistant professor there and got tenure there. And then more recently in 2019, she moved over to Penn State as associate professor. So Kelly already has a fair number of awards given her efforts. She was awarded the Office of Naval Research Young Investigators Award program. She's received an NSF Career Award for her efforts, and more recently an Outstanding Early Career Award from the AMS for the mesoscale processes, part of that thing. So Kelly, as she'll be showing you today, spent a lot of time looking at coastal convection, which is a very difficult problem for many reasons, as she'll probably point out. There's been a lot of work in the Central Plains and other areas, but not nearly as much work just off the coast. And she uses a lot of observations and idealized models. And so I think, and she's been involved in ESCAPE this past summer, and then even down in Argentina, there was a field experiment. So let's welcome Kelly. She's going to talk about the behavior of squall lines over coastal zones.
Is that okay? Everyone can see this all right? I know I have like Zoom faces there and everything, but to go back and fix this will probably take some time for me to
I think this slide. Oh, this is a blackboard.
Yeah. All right.
Is everyone dizzy?
We're going to say that. So thank you so much. It's wonderful to be back. It's wonderful to see familiar faces and get to chat with people. So I really enjoyed my visit so far. So thank you. So today I'm going to be talking about squall lines over coastal zones and all aspects of that. And I want to acknowledge my postdoc Fan Wu and a former master's student Tristan Kading for working on this project with me, or projects. So just to start with some basics, my group looks at the impact of surface and lower tropospheric heterogeneities on organized deep convective storms known as squall lines. So sometimes they're referred to as quasi-linear convective systems, sometimes mesoscale convective systems or MCSs. And there's just two plan views of squall lines depicted through radar reflectivity. So of course we have our quasi-linear narrow band of high reflectivity here. Hopefully you can see that. So that's the leading convective towers, and then often trailed by, kind of moderate stratiform behind that, but obviously that's not always present. Okay. So my focus is largely on storms over the coastal zone, as you know. So I'm specifically looking at the behavior of squall lines as they move from inland regions towards the coast and then potentially offshore. And so squall lines occur over a number of coastal regions globally. A bunch of those I have highlighted there in the purple boxes. And many of these areas actually have mountains at or near the coast, which also impact storm evolution. And so also mountainous coastlines can exhibit variability in the topography, both in height, as well as the distance of that mountain chain from the coast. And so if we just look at an example like the Appalachians, if we look at the northern portion of the Appalachians, they basically butt up right against the coastline, right? New Jersey, New York coastline. When we look further south, they're displaced much further inland, and instead we have this nice flat coastal plain right next to the water. And so we seek to understand squall line response to sea breezes as storms move over those flat coastal plains, as well as over coastal mountains before they start interacting with the sea breeze. And so as squall lines move towards the coast and encounter sea breezes, right, so they're encountering that stable marine atmospheric boundary layer air, some interesting changes can occur in storm dynamics, the evolution and life cycle, the intensity of the storm, and coastal precipitation. And so I just have a few examples of these evolutions through radar reflectivity. So one, perhaps maybe the most commonly thought of one, is that, storms basically reach the coastline, they can decay. Okay. But that definitely does not always happen. Sometimes they can intensify at the coast, which you can see down here in the New Jersey area. And so that'll run through again right there. They can also do something called a discrete propagation, where you have isolated cells that actually form ahead of the main storm along the coast. Those actually grow upscale and they become the new leading convective line of BMCS. So it looks like the storm actually jumps forward. And in situations like this, the storm is actually going to arrive at the coast sooner than expected, just from that anticipated, or measured translational speed alone. And so understanding which of these evolutions takes place is important for hazard prediction. So what can these do? They create flooding, lots of flooding. They can create small hail, high winds, frequent lightning, as well as tornadoes, and of course at the coast, waterspouts. And since obviously the populations are often clustered at the coast, these are going to be high impact severe events. And so today I'm just going to be talking about one societally relevant result from the work we're doing. And specifically, that's the coastal precipitation maximum. And so as squall lines move from inland regions towards the coast, there can be an increase in precip. And this can occur either before the storm encounters the sea breeze or while the storm is encountering the sea breeze. So some fundamental questions I'll be addressing today are: under what conditions will we see a coastal precip max? When and where will it occur in relation to the squall line evolution? And what are the driving physical processes? And so it turns out that different physical processes can cause coastal precipitation maxima, which results in obviously a different precipitation evolution, different hazard evolution. And the different physical processes that can cause these different types of coastal precip maxes depend on the base state environment. And it also depends on whether the coastline is flat or mountainous. Okay. So before we get into how the coast and the coastal mountains influence our storms, I just want to reminder of some basic squall line dynamics. And so here again, I just have the radar reflectivity in the lower left and just a schematic cross section of a squall line on the right. And so we see our updrafts in red, our downdrafts in blue, and then our cold pool at the surface. And so squall lines are self-organizing multicellular deep convective storms, which means that they're sustained through the continued generation of individual convective cells on a preferred flank. Okay, and the important part is the individual convective cells. And so we get evaporation of storm precip that generates a downdraft. When the downdraft reaches the surface, we get the development of our cold pool. That's often referred to as a thunderstorm outflow or a gust front. And as the cold pool moves across the surface, that's what provides the lift for those individual convective cells, which is necessary obviously for the maintenance of these storms. Okay, so CI by the cold pool is going to be important. And in fact, it's critical for squall line maintenance. Okay, so today we're really just going to focus on how sea breezes and coastal mountains can impact this CI and therefore squall line evolution and coastal precip. Okay, so how can our sea breezes and our coastal mountains impact CI and our coastal precip? Well, I'm going to step through a couple of basically kind of fundamental ideas that I'll be addressing a little more specifically through the talk. And so one, storms can destabilize their surrounding environment. And that actually allows sea breezes to initiate convection. Okay, well, what does that mean? Well, for one, again, we just have a schematic cross-section of a squall line. So precipitation can fall from the forward anvil of a squall line. And in the lower left is just a snapshot image of a deep convective storm anvil and kind of this fuzzy area. It's actually falling precipitation. And so the evaporative cooling underneath a squall line anvil can actually decrease the lower tropospheric conditional stability ahead of the storm. And to illustrate that, this is a cross-section from some of our idealized numerical simulations of a squall line moving towards the coast. And so shaded here is theta ES. The black contours are U magnitude, so the wind magnitude. The precipitation mixing ratio associated with the storm is in this green shading. And then the blue marks regions of negative buoyancy, and that basically highlights our sea breeze here, right? So the storm and the sea breeze are moving towards one another. And you'll notice that there's this area of low buoyancy or negative buoyancy that's located pretty much right under the squall line anvil. And also notice as we look at the theta ES moving towards the storm, it decreases, which means that we've just increased the conditional instability right ahead of the storm. And so this reduction in stability is going to be favorable for that CI that we need for our squall lines. So in addition, we can get a decrease in stability through storm-generated gravity waves. And so deep convective storms generate gravity waves of a bunch of different frequencies. And so this animation just shows the generation of a buoyant updraft in an idealized model through the insertion of a warm bubble. So just put a warm bubble in there and you see we get this vertical motion here. So buoyancy is shaded, red is positive, blue is negative, vertical motion is contoured, where positive is solid and negative is in dashed. And you'll notice as the plume goes up, we see these oscillating, up and down patterns, which I'll have a still shot soon, but up and down patterns associated with the waves. And so some of the waves that these storms generate are low frequency or n=2 gravity waves. And they're basically generated in response to the storm latent heating serving as a broad heat source. And so on the bottom right, we have a schematic cross-section of one of these n=2 waves. And the characteristic vertical motion associated with these waves is a vertically stacked couplet of opposing motion. So for example, in one branch of the wave, we'll have ascending motion in the lower troposphere, and then we'll have descending motion in the upper troposphere. And so this lower tropospheric lift here can actually lift the atmosphere and temporarily cool the mid-levels, decreasing the lower tropospheric static stability, which again is going to be favorable for CI. Okay, so this is actually going to move ahead of our storm. So as our storm approaches the coast, our onshore moving sea breeze can move into this area of reduced stability and initiate cells ahead of the squall line in this less stable environment. Okay, so that's one way, which means that we have an additional source of CI ahead of the gust front now, which is going to change our squall line evolution, lifetime coastal precipitation patterns in this regime. All right, so that's one. Two, those storm-generated gravity waves can actually interact with sea breeze-generated gravity waves, and those can initiate convection. And so in addition to our low frequency or kind of long wavelength waves, gravity waves, storm can actually generate high frequency gravity waves as well in response to fluctuations in that latent heating that I talked about. And so like I promised, here's a still snapshot of that animation I showed earlier, and you see the ascending and then descending patterns associated with these high frequency gravity waves and the associated buoyancy patterns too. There we go. So in certain environments, those waves generated by the squall line can become trapped in the mid-troposphere, and they can propagate well ahead of the storm. However, sea breezes can also generate gravity waves, vertically propagating gravity waves. So again, here's a cross-section from an idealized simulation of a coastal squall line. And so our storm, again, the precipitation mixing ratio is in green. Our sea breeze is shaded in blue, so that's the buoyancy. Vertical motion upward is contoured in blue, downward is contoured in red, and then this kind of Neapolitan ice cream thing in front are passive tracers that we released. And so you can see this up, down pattern in both the vertical motion and the squiggly passive tracers associated with the gravity waves that are being initiated by basically our sea breeze moving along. And so the high frequency gravity waves from the storm can interact with the lower tropospheric gravity waves generated by the sea breeze. And together they can create deep lift and can create CI ahead of the squall line. And the squall line cold pool. So once again, we have another way that we can get CI ahead of our gust front, which is going to impact our coastal precip pattern. And if you remember, in front of the storm, we have an area of reduced stability, so that's also going to help support our CI. So third, our cold pool sea breeze collisions, they can happen and they can initiate convection. And so the collision between these two density currents results in enhanced convergence and then enhanced ascent at the gust front, which lead to CI then becomes more likely. It can lead to more intense precipitation, and therefore we're going to impact our storm evolution and our precipitation. But changes in squall line precip in turn then also change the cold pool characteristics, which can also change CI. So that's kind of just a nice feedback loop that we have to worry about as well. And so another thing to consider is that once the cold pool and the sea breeze approach one another and meet, the density gradient across the gust front actually decreases. And this will impact the trajectory of rising air parcels once they're initiated, which is going to impact our updraft slope or the updraft intensity, our squall line lifetime, and our coastal precip patterns. So, and the last one I'll touch on is mountain sloping surfaces. So those can actually modify the cold pool characteristics, which is therefore going to impact the ability of the cold pool to initiate convection. And so as the cold pool and the storm move up and down the sloping mountain surfaces, we can get changes in cold pool depth and we can get changes in cold pool buoyancy. So for example, as our cold pool moves up a mountain slope, they typically deepen and become denser due to the gravitational deceleration of the dense cold air. And then we also have enhanced precipitation associated with orographic lift. When they move down the mountain slope, though, they become shallower due to gravitational acceleration and less dense because it adiabatically warms. And then once it reaches, say, the mountain base or flatland, the cold pool can deepen rapidly and become denser. And then obviously that's going to change its ability to initiate convection. And so changes in these cold pool characteristics are going to impact, obviously, gust for ascent, sea ice success, and storm evolution and precip. And just as an example, this is both a cross-section and a plan view of a storm that's initiated over a plateau top. So the terrain is this gray. And then the storm is going to attempt to move down the bottom. So again, this is from idealized simulations. And so initially, we have a very mature heavy squall line sitting on the plateau top. As it approaches the edge of the plateau and the cold pool starts to move down that slope, we get a reduction in storm intensity because of the thinning, and the cold pool is less able to generate convection. Then eventually the cold pool reaches the mountain base, we get CI, and notice that continues to grow upscale. So essentially we get the regeneration of the storm once it reaches the mountain base. Also, as storms move up and down the mountain, they're going to encounter different thermodynamic and kinematic conditions, right? The kinematic and thermodynamic conditions at the top of the mountain are going to be different than the bottom. That's also going to impact our storm as it moves over mountain slopes. And for squall lines moving over coastal mountain chains, all these factors have to actually be considered. And interestingly, the combined influence of a sloping mountain surface and a sea breeze together actually yields different storm behavior than storm response to each one of these separately or alone. Okay. And so what we're trying to do is understand the physical processes driving coastal squall line behavior, identify the supporting environments. We're trying to identify robust similarities and differences that occur across a broad range of environments, sea breeze conditions and mountain conditions. But how do we manage all these complexities? Well, as you probably have guessed, and as Brian alluded to, we use idealized numerical modeling experiments to simplify this complex problem. And so it allows us to isolate the impact of a parameter space of sea breezes, different mountain characteristics, different thermodynamic and wind vertical profiles on our storm behavior and the storm precip. Okay, and that's what I'll primarily be talking about today. And so we use the NCAR Cloud Model 1. So it's a cloud resolving model. We perform experiments in both 2 and 3D. Our horizontal resolution is 200 meters, so the grid spacing is small. Vertical resolution is actually 50 in the lowest 3 kilometers of the idealized model, and then we stretch it to 250 by the model top. And so thus far, we've used 2 different kinematic and thermodynamic conditions in the model. Okay, so you basically initialize these models by just plopping in a sounding. Okay, so it's uniform. So we've used what we call a mid-Atlantic profile to initiate the idealized simulations. And that's actually based on observed profiles that support coastal mid-Atlantic MCSs. But it's also representative of coastal environments that support squall lines in different areas as well, besides the mid-Atlantic. So we have a surface base cape of about 1,500, and our wind shear is about 15 meters per second in the lowest 3.5 kilometers. We also use what we call a long-lived sounding, which people may be familiar with. And it's designed to support long-lived MCSs. So this is the classic Weizmann and Klemp 1982 sounding. And so here the SP cape is a little bit higher, 1,900 joules per kilogram, and the wind shear is lower, 10 meters per second over the lowest 2.5. Okay, so first, we're going to talk about experiments that only have a sea breeze in it. So we're going to put the mountains on hold for now. And so for these initial experiments, we initialize the sea breeze by just inserting a big cold blob, a negative potential temperature perturbation block of cold air in the right side of the domain. And that's how basically we imply our coastline. And so we choose this method because it allows for control over the marine layer depth and the marine layer thermal perturbation that's going to be driving our sea breeze. So we do use other sea breeze initiation methods, but I'm going to talk about those later on. And so on the left side of the domain, we initiate our squall line, and then the two move towards each other. Okay. And so we perform 2D idealized simulations first using that long-lived sounding. We use marine layer potential temperature perturbations between -2 to -8. So those three here. We use different marine layer depths, 250, 500, and 1,000 meters. And then we perform three-dimensional simulations using that mid-Atlantic sounding that I've talked about. And so for that, we use a reduced number of marine layer theta perturbations and depth, just basically informed by our 2D squalling simulations. So we didn't feel like we had to do as many of those. Okay, so we're going to think about the mid-Atlantic experiments first. And so this is a plan view of precipitation mixing ratio, snapshot in time from those simulations. And at this time, 195 minutes, so in the upper left, this is just before the storm and the sea breeze collide. So this is when they're close to one another, but they haven't necessarily, the cold pool hasn't collided with the sea breeze front yet. And you'll notice that there's this field of isolated cells that form ahead of the main convective line. So basically over the sea breeze. Those eventually organize, grow upscale, and they become that new leading edge of the storm. And so that's our upscale growth or discrete propagation that I mentioned earlier. And just, for reference, no CI occurred when the squall line and the sea breeze were far from one another, or if we just had the squall line in the domain with no sea breeze. And so this generation of cells actually creates a coastal precip max about 20 to 30 minutes before the collision of the squall line and the cold pool. So here's a time series of total mass of rain in the domain. For the control in black, deeper marine layer experiments are in solid, our more shallow ones are in dashed, and then our very cold theta perturbations are in blue, and our less cold theta perturbations are in red. And so notice that there's a peak in precip before the approximate collision time, which is marked by this gray line here, the approximate collision time between the cold pool and the sea breeze. And so notice that this increase occurs for all storms, and interestingly, it actually occurs, the largest peak occurs for interaction with the deepest and the coldest sea breeze. So not collision, we did not collide. All right, so that's what happened in the mid-Atlantic experiments. So what about simulations where we use just that long-lived profile, right? So a different environment. Well, we do get that CI and discrete propagation, but we only do for a subset of the experiments. And it's only for those that are associated with the deepest sea breeze. So here are, again, cross sections of precipitation mixing ratio. So our storm is on the left. Our sea breeze is actually this black contour here. So that's actually the buoyancy. That's on the right. And in these panels, the sea breeze gets, cooler as we move down, and it gets deeper as we move from left to right. So in this last column here, this is all of our deepest marine layer scenarios or simulations. And notice that we do get CI out ahead of the storm and not so much in any of the other simulations. So what processes just drive this discrete propagation in each of these environments? And then why does it only occur for a subset in long-lived storms, but it occurred for all of the mid-Atlantic storms? So it's because of the propagation physics, and the propagation physics are actually sensitive to that base state. And so for our long-lived storms, the sea breezes were too shallow to lift parcels to the base state LFC, which is around 1796 meters. But as the storm and the sea breeze approached one another, a subset of sea breezes were then deep enough to lift parcels to a new lower LFC, which was around 840 to 890 meters. And it's because the LFC was lowered in that storm modified environment, right? In that storm environment that became more unstable. Okay, and so our 1,000-meter deep marine layer was all of a sudden able to lift parcels to this new lower LFC. Okay, but the other two were still too shallow, so we did not get CI. For our mid-Atlantic storm, CI had nothing to do with the lowering of the LFC. It was actually due to that constructive interference of gravity waves generated by the storm and gravity waves generated by the sea breeze front. And again, this all occurred, the meshing of these all occurred within an environment of reduced stability. And because of that, all of our sea breezes in these simulations actually supported CI. Okay, so the base state was important in this particular instance. All right. It's funny, I was about to ask questions. If anyone had any questions, I fell into like teaching mode for a second. We all good? All right, so those are our sea breeze only experiments. So now I'll be focusing mostly on, for the rest of the talk, the sea breeze and coastal mountain experiments. Okay, so for these, we put in a plateau, which you might have guessed from the image earlier. So we put in a plateau with a slope that leads down to our sea breeze. So it's obviously a simplified representation of coastal terrain, but generally speaking, it's a pretty commonly observed structure of the coast. And so we use 3 different plateau heights today. I'm just going to be talking about the middle of the road one that we use, the 1.5 kilometers high plateau. And we're going to initialize, again, these idealized simulations with that mid-Atlantic sounding that we use for those sea breeze experiments. Okay, so the same environment we're going to be using for this. And so again, we insert our sea breeze as a cold block. We performed more exploratory 2D simulations using a wider range of theta prime and marine layer depths. And then we performed some 3D simulations with a reduced number, again, informed by our 2D simulations. And so the edge of the marine layer was basically, at the edge of our quote implied ocean, which allowed then the cool air to slosh towards the slope of the mountain. Okay, so it moved towards the mountain as a sea breeze. So here's an animation of our 1.5 kilometer plateau and one of our colder, deeper sea breezes. And so we have our mountain, or our squall line at the top of the mountain moving down and interacting with the sea breeze. And so when we include a mountain, no discrete propagation actually occurs. Okay, in the same environment, we don't get a discrete propagation, but we do still see a coastal precip max over the mountain slope. And here it's actually due to the collision between the squall line cold pool and the sea breeze front. So that scenario that I described earlier. And so here are time series for all of our 2D experiments in max vertical motion, total precip mass, and then total rain rate. And so the browns are the shallow sea breezes, the magentas are kind of moderately deep, and the blues are our deepest, and the black is the control. And so this little red line here actually marks the range of cold pool sea breeze collision times for all the experiments. So it's there just for reference. But notice that there's an increase in vertical motion at the time of the collision. And following that, we get an increase in precip mass and then rain rate. Okay. And interestingly, the greatest vertical motion and total precip and rain rate actually occurs again for our deepest and coldest marine layers. And so you can see that the blues are kind of hanging out above everybody else, right? And those are our deepest marine layers. And just kind of zooming in to show you this a little bit more explicitly, here are cross sections of precipitation mixing ratio over the slope when we have no sea breeze, and then our strongest sea breeze. And so notice when we have our strongest sea breeze, we get this nice deep convection over the slope as the cold pool collides with the sea breeze. And if we have no sea breeze, it's kind of wimpy. But do note, I actually we kind of skewed the total mixing ratio for our precip to higher values just to kind of accentuate this difference a little bit more. Okay. So here, what processes drive the coastal precip max, and why is the max greatest for the deepest and the coldest sea breezes? Well, we have to think about some pressure perturbations for this. So at the bottom is a cross section of pressure perturbations. And so positive pressure perturbations are shaded in red, negative are shaded in blue. What's contoured in black is actually the vertical acceleration. And so positive vertical acceleration is in the solid and negative is in dashed. And so this dashed line marks the cold pool front. And notice that we're pretty zoomed in, right? This is 0, -4 kilometers from the cold pool front, and then plus, and in the lower troposphere. And so convergence at the gust front is always associated with a positive non-hydrostatic dynamic pressure perturbation, right? And so this P prime basically drives an upward acceleration, which we see by the black contours, and potentially precipitation. I forgot I had all these pretty things. But okay, that's only part of the story. But there's also buoyancy gradients across the gust front. And this is represented or shown, illustrated through a cross section of theta E. Okay, so this is our cold pool, and this is the ambient air that it's moving into. And so, oops, jumping the gun. So this baroclinity is actually associated with the generation of horizontal vorticity, which we can see in this cross section here. So I'm just trying to highlight that with this arrow. So because of this buoyancy gradient, we get the generation of horizontal vorticity, and horizontal vorticity is always associated with a negative non-hydrostatic dynamic pressure perturbation, which means that if we have our air parcels rising up from our convergence, they actually get shoved back down by our negative pressure perturbation and the downward acceleration associated with that negative pressure perturbation. And so that's what happens if we do not have a sea breeze present. What happens if we have a sea breeze present? Well, we still get that strong non-hydrostatic dynamic pressure perturbation and vertical acceleration at the sea breeze front. But now if we look at the theta E cross section, notice that the buoyancy gradient is reduced. And so that means that we're going to have less baroclinically generated horizontal vorticity. We're going to have a smaller, I should have pointed this out probably a little bit more in the slide before, but a smaller negative non-hydrostatic dynamic pressure perturbation, right? We have light blues here before we had dark blues, which meant it was much stronger. And therefore we have a stronger, or I'm sorry, a weaker, there we go, a weaker downward acceleration, right? Not so many contours in that dashed line here. And so because of the fact that we have that reduced buoyancy gradient, this is actually going to allow parcels to rise up and continue and lead to intense precipitation. And so that's why we have intense precip during the collision process with the most intense cold pool, or I'm sorry, most intense sea breeze, and we had really kind of wimpy precip when we did not have that. Okay, all right. So as I promised, we're going to think about other ways to initiate the sea breeze. And so in the research and operational communities, sea breezes are initiated through a variety of different ways. And so the question is, will using different initiation mechanisms impact coastal squall line behavior? Yeah, it will. So we tested 3 other sea breeze initiation methods that are commonly used in the literature. And we use it in our coastal mountain environments. We're going to keep the same mountain. We're going to keep the same mid-Atlantic profile. Okay. So what are the other ones we use? Well, one is a sensible heat flux function, which is maximized actually at the plateau top and decreases moving down. And so this is a diurnally varying sensible heat flux function over the land area. We chose 3 peak values of 100 watts per meter squared, 150, and 200 watts per meter squared. Over the ocean, we just had a constant 10 watts per meter squared, okay? And all of these maximum values, or H0 values, were actually based on ERA 5 reanalysis of the Mid-Atlantic region. Okay, so these were quantified. Then we also perform experiments where we include a latent heat flux function as well, which is especially important because right we're near the water. And so we still have our sensible heat flux function, but now we're adding the latent heat flux function as well. And so here we just use one H0, so max values at 240. And then over the water, we're adding a latent heat flux that's constant, so not diurnally varying, of 60 watts per meter squared. And then finally, we're using what's probably more common in operational models and mesoscale models for research, and that's a surface layer scheme. We're specifically using the MYNN in case you're interested, and then we're using radiation, right? So long wave and short wave radiation that's parameterized by the RRT-MG. And so our surface we defined as a mixed forest, obviously. That's for land, the land surface of our mountain. Obviously, we have a water surface over our implied ocean. And here, the magnitude of the sensible heat flux is primarily due to wind speed and then the difference in the potential temperature from the surface to the overlying air. And the latent heat flux is primarily influenced by, again, wind speed and then the difference in mixing ratio between the surface and the overlying air. All right, so we're just going to think about these sensible heat flux functions, latent heat flux, and what we're calling the radiation experiments. Okay, so we're shelving the marine layer for now. At the bottom left is a plan view of yeah, hopefully you can see that. Our sensible heat flux function with a max of 100 watts per meter squared, then 200 watts per meter squared. This is the sensible plus latent, and then this is our radiation scheme. On the right-hand side is the same thing, but just cross sections. And notice that the coastal precip enhancement is pretty minimal when we look at anything with a sensible heat flux function, right? We still see some precip, but it's pretty weak. And in fact, we see mostly a precip maximum only for the surface layer scheme with radiation. Oh, I have it highlighted there. So why is there no CI over the slope with a sensible heat flux function? So it's because the cold pool actually is dissipated by the sensible heat flux function. And so this is a cross section of theta E while we're over the plateau top. Okay, so this is where the cold pool may be. And this is for our surface heat flux function experiment with a max of 100. And this blue shading here is what's supposed to be the cold pool. And so the cold pool actually dissipates prior to reaching the edge of the mountain slope, which means that it can't go anywhere and collide with the sea breeze because it doesn't exist. Okay, and this is due to the continuous heating during the day from the prescribed function. So it is diurnal, but it is, a heat flux function we're prescribing. And so we can see that by looking at the sensible heat flux magnitude with horizontal distance. And this is at noontime. So we did define hours. This is at noontime. So it's 4 hours after we initiate our heat flux function. This is basically the time we're going to have the peak. And so the plateau is on the left-hand side. The slope is actually bounded by these gray dashed lines here. And then the ocean is on the right-hand side, right? So this is our full X domain. And so what's in the blue is the magnitude of the sensible heat flux function with a max of 100 watts per meter squared. In magenta, it's the same, but for the 200 watts per meter squared. And you see at noontime, right, we're sort of maxing out each one of those functions. So it's being continuously applied to the cold pool and it weakens it. So if we think about the surface layer scheme with radiation, the surface layer scheme is actually interactive. And so as it moves over the surface, or as the cold pool moves over the surface, it actually cools the surface. So the surface temperature is going to respond to the movement of, or the passage of the cold pool. And so we can see that in our sensible heat flux distribution, right? And so the red is the radiation experiment that I've been referring to. And notice when the cold pool passes over, which is this time here, we see a dip in the magnitude of the sensible heat flux. And so we're down, even below 50 watts per meter squared. And just for comparison, in green is the same type of experiment. So, using the same radiation, surface layer scheme, and initial conditions, but we have no convection. So this is where it should be at if the cold pool did not, was not passing over. And so because of that, the surface heat flux into the cold pool is reduced. The cold pool successfully moves down slope, which you can see it here in our theta E. It's going to collide with our sea breeze, and therefore we get really robust CI over the mountain slope. Okay, so we want to know, so we have this dissipation of the cold pool, and we want to understand how sea breezes initiated through different mechanisms are going to impact our coastal CI. But if the cold pool dissipates, right, we can't do that. Oh, there we go. And so if we look at these cross sections with their upslope wind speed for our different experiments, so the top two are through time. A marine layer experiment with sort of shallow and weak, a marine layer experiment deeper and colder. Here, the next two are surface heat flux experiments, surface heat flux function experiments with 100 watts per meter squared and then 200. This row here is a sensible heat flux function plus our latent, and the bottom is radiation. But most importantly, I want you to kind of focus on this last column here. And so notice that there are quite a few differences in the magnitude of the upslope wind speed associated with the sea breeze, the inland advancement, right? Some are further up the slope than others, and then also the depth. And so if we have a cold pool dissipating, we can't quantify how these different types of sea breeze characteristics are going to influence CI, okay? And further, the physical processes driving the upslope sea breeze flow actually vary for initiation mechanism. And so what's shown here is a time series of basically the local change of wind, so our upslope flow or our sea breeze flow. And then we have the contributing processes to this local change. And so those processes are advection or perturbation, pressure gradient force, and buoyancy. And so the blue lines show the marine layer experiments, the magenta show the surface heat flux function experiments. The brown dashed is when we have our surface heat flux plus or sensible heat flux plus latent heat flux, and then the radiation is actually in the solid. And I just want to point out two things. One is when we look at the buoyancy plot, notice that for our marine layer experiments, it contributes negatively to the upslope flow. But for the other experiments, it actually contributes positively. Okay, so there's a different mechanism driving the sea breeze here. And also, which probably makes sense, we see differences in the perturbation pressure gradient force as well, which contributes positively in our marine layer experiments and actually negatively in our other, sensible and latent and radiation experiments. So we're interested in quantifying the impact of these differences now on CI. And so to do that, rather than initiating a storm, we just plop an artificial cold bubble at the top of the slope, and that's going to be our cold pool. And so here's just an example. We basically dump this little pool of cold air up here, let it run down the slope, and so we don't worry about initiating a storm. And so there will be some minor modifications to the cold pool as it moves down the slope, obviously by the surface fluxes, but not enough to impact anything dramatically. And so we feel this is a pretty viable method to use. And so when we look at the relationship between sea breeze type now and CI, we get a different answer. And so here we have the marine layer experiment returned. And so we have our deep marine layer experiment, deep cold here, a sensible heat flux function of 200 watts per meter squared here, sensible plus latent over here, and then our surface layer scheme plus radiation here. And now we see that the sensible heat flux and the sensible heat flux plus latent heat flux are actually the strongest of the two, and they generate the strongest convection. Well, why is that the case? Well, we're going to think about our vertical acceleration again. And so just focusing on these two plots here. So this is our sensible heat flux, our sensible plus latent heat flux down here. The dashed line again shows the location of the cold pool front. And so the shading is the vertical acceleration, where red is positive and then blue is negative. And then the contours in black show basically the dynamic acceleration, you can call it inertial. And so the contours in purple show the buoyant acceleration. And that's the part that I really kind of want to emphasize. And so notice at the cold front, at the leading edge of the cold pool front, we actually see some really strong vertical acceleration in the two experiments, right? And in part, this has to do with the fact that, the colors are a little washed out there, so I don't know if you can see it, but there is a lot of contribution due to positive buoyancy because of the way these sea breezes were initiated and generated. And so the positive buoyancy associated with the generation of the sea breeze actually contributes positively to the vertical acceleration at the sea breeze front. And so if we look at the radiation experiment, right, it did so well before and it didn't do that well now. Well, why is that the case? Well, actually, in part, it has to do with the fact, which I don't think I pointed out, but I'm gonna rush back there anyway. If you look at the magnitude of the upslope flow or the sea breezes, right, the radiation sea breeze is actually pretty deep and probably one of the strongest, right? And so that's actually a problem. So if we look at again, processes, we see vertical acceleration at the leading edge, but it is more shallow than compared to the other two experiments. And then we also see the presence of negative acceleration here. And that actually helps drive parcels back down. And that caused that curve shape, which I know I'm wasting time doing this, but I really want to show you this curve shape here of the parcels. And so where does this thing come from? Well, it actually has to do with the magnitude of the sea breeze. And so the sea breeze actually enhances the vertical wind shear. It creates a negative dynamic pressure perturbation, downward acceleration, and it causes those parcels to descend. And so we don't get that deep lift anymore. All right, so that was a crash course on Squall Dynamics. And so for the final part, I just wanted to touch briefly on some of the climate work we've been doing related to coastal squall lines. So there is a thread for everything. And we're looking at coastal squall lines over the eastern seaboard in a future climate. And so why are we doing that? Well, there's a number of studies that suggest that the severe thunderstorm environment in this area is projected to increase in the future, both through just looking at a CMIP ensemble and looking at dynamically downscaled CMIP models, say using the WARF. And so this red basically implies that there's going to be more favorable environments or an increase in the number of days that have a favorable environment for severe weather. And favorable environment is basically the combination of a vertical wind shear and a Cape multiplication. Okay, so that's good, but we don't know any of the storm scale details if we just look at the environment. We don't know if the storms will even initiate in this environment. We don't know the storm mode. That could change, and that's important for hazards. If we do get a squall line, we don't know about storm intensity or lifetime. We don't know the coastal evolution. We're actually going to have changes in the coastal ocean, which is going to influence our marine layer and our sea breeze. And then we don't know much about, we have all these mountain processes. So what's going to happen when these storms try to cross a mountain? Will that change? And so to address some of these storm scale questions, we're using what's known as the pseudoglobal warming approach. And I'll just give a very brief crash course in what that means. And so basically we're using mesoscale models to simulate historical squall line events. And so I have a radar animation of one of the events that we're simulating here. And so we're going to simulate it in historical time, but we're also going to simulate it in, what we call a future time. And I'll explain what that means in a minute. And so comparison of these historical and future mesoscale simulations of our case allow us to quantify the storm scale changes that might occur in a future climate. And so for these, we're moving away from the CM1 and we're using the WARF. We have a nested 3 kilometer, 1 kilometer grid. And the example I'm showing here that I'll be discussing is an Eastern US squall line event. Obviously, you probably know that. And it occurred on May 14th of 2018. And for this event, we actually tried to choose events. We have a few others we're looking at. But storms that actually cross the Appalachians and encounter the coastline. And so we can look at all those processes together in these simulations, which is nice. Okay, so the pseudoglobal warming part. So for our historical simulations, we're just initializing our model, our WARF model with the HRRC, right? So the high resolution rapid refresh. And so for the climate, we take the HRRC and we're going to add a climate perturbation and then run the WARF again. And so the climate perturbations are based on the CMIP6, and they're calculated by taking the difference in variables between a 10-year average and a future period. And so our mid-century is 2045 to 2054. Our late century is 2090 to 2099. And so we average 10-year periods there. We also average, our historical period. And so the difference between our future and our historical gets us our perturbation. So the historical is from 2005 to 2014. And we only do this for the month that the event occurred, right? So we don't get winter mixing in with this. And so we only take 10-year averages of May alone, okay? And we do this for all of the CMIP 6 variables that we have. And so first, we just wanted to quantify, what are the changes in our storm due to atmospheric variables, specifically temperature, moisture, and wind, due to SST, right? Because the CMIP6 has that. And our soil variables. So do we see changes in the storm due to each one of these things? And so that's what's shown on the right-hand side here. So here are time series of all of our experiments, which again, might be a little washed out. And so the control is in black. I will tell you it's up here. The atmosphere experiments are in blue. The SST experiments are in green. The soil experiments are in this brown color. And then red is when we smush them all together. And so our historical period are the solid lines, and then our historical period are mid-century. So mid-century minus historical for the perturbation. Our mid-century is in solid, and our late century is in dashed. And so one thing you'll notice is that, the soil and the SST simulations basically parallel the control, which means that, this is, I should mention, trying to squeeze it all in. Composite reflectivity and area of average rainfall in this box here. So it's going to be a squall line following box. And so we can actually quantify the changes in precip as it moves over the mountain and then over the coast. And so the soil experiments and the SST experiments are pretty much like the control. And so in that respect, they don't seem to have much of an impact, at least in this particular case. But our atmosphere experiments and all experiments actually do impact things. And I do want to mention that we actually, tried an active ocean. We performed what we call extended SST and soil simulations, which is simulating things basically a full diurnal cycle earlier. And there wasn't that much of an influence or change. So let's just think about the atmosphere only and our all simulations, since they had the greatest impact. And so I highlighted the time when the storm was crossing the Appalachians. And so there is a decrease in precipitation intensity when the storm is over land during the mid-century, which is up here, and the late century, especially, which is down here. When it moves over the coastal plain, though, notice that these differences start to collapse as the storm basically approaches the coast, at least in the mid-century. And by the end, notice that during the coastal crossing period, that there's actually little difference in our kind of mid-century storm and our historical storm. The storm is weaker in the late century, but it was a little surprising to see that there wasn't much of a difference in the mid-century. And so this might actually have to do with the speed of it weakening as it crosses the coast. And so here's just a couple of snapshots of composite reflectivity from the present day as the storm moves offshore and the mid-century when the storm moves offshore. And notice that it's actually more robust in our mid-century simulation compared to our historical simulation. Okay, so that might be why, but we're looking into it. And then some final experiments that we're working on now are basically ranking the CMIP6 members. And so what does that mean? So we calculated tropospheric deep temperature, specific humidity, U-wind and V-wind perturbations for all of the models. And then basically we used their interquartile range and classified them as like a weak perturbation, kind of a middle of the road perturbation, or an intense perturbation. And so we have these subgroups now. Each of them have 8 or 9 members. And so we apply these then to quantify storm response to the climate perturbations of each of these subgroups, right? So what if we have an intense perturbation, or what if the perturbation isn't that strong? And so I just wanted to show you what these perturbations look like tropospherically. And so we rank them based on the tropospheric average, but we apply them, we retain the tropospheric perturbations. And so the temperature perturbations are up in yellow in the upper left. And so the dashed lines are the mid-century perturbations, the solid lines are the late century perturbations, the weak perturbations are in blue, the middle are in black, and then the most intense are in red. And so for the temperature, notice there's actually kind of like a bimodal distribution of the increase in temperature. When we look at specific humidity, there's just basically an increase in specific humidity near the surface, both through our ranking method and also through time. For U-wind and V-wind, for U-wind, there's maybe a weakening trend in the westerlies. V-wind, maybe a tendency towards more southerly winds. But since we're averaging for 10 years and we're averaging for a whole month, we might actually be smearing out daily wind patterns that are important. And so I'm not going to talk about the wind experiments. I'll just touch briefly on our temperature and our specific humidity experiments. Okay, so first we apply individual climate perturbations to the historical HER values, okay, or HER initial fields. And so we apply, one simulation, we only apply an intense temperature perturbation. Another one, we only apply an intense moisture perturbation, okay, and that's what's shown here. So the top 2 are for the mid-century, the bottom 2 are for the late century. And looking at these, it's pretty easy to understand what's going to be happening in the future based on this, which is why we did this. We're basically testing each variable individually to simplify the interpretation. And so apply that temperature perturbation, storms basically vanish. Apply that moisture perturbation, storms go, crazy, basically. And so that's one avenue we're exploring now. And then just finally, the other avenue is actually we're adding the ensemble mean climate perturbation to 3 of the variables. And then we're adding either a weak or intense to one variable. And so we're adding the ensemble mean to say, our winds and our temperature, but then we add a strong moisture perturbation or a weak moisture perturbation. And the benefit of that is that we can quantify the combined impact of these variables in a future climate. And when we do, either a weak or intense perturbation, we're actually testing the range of sensitivity of one particular variable. And that's what's shown here. And so if we have a weak moisture perturbation, with everything else being the CMIT mean, looks pretty sad. Intense moisture looks much better. If we do weak temperature, looks pretty good. If we do intense temperature, not so great. And so the very oversimplified interpretation of this is that when our moisture change is smaller than our temperature change, so if we have weak moisture and a mean change in the temperature, our storms are really weak. If we have a temperature perturbation, basically that's smaller than the mean moisture change, or I should say the moisture change, because this is mean and this isn't, but essentially we get a nice storm. And so there's definitely going to be a competing impact of temperature and moisture for these storms in a future climate. And looking at this, it's going to be pretty hard to say whether one is going to rule out over another. But right now we're, this is very new work, and we're digging into the storm scale processes. So with that, I will just leave up my summary here because I know that was a very packed, I got really excited. And I thank you very much for your attention for all of this stuff, and I'll take any questions if you have any.
Okay, we'll do questions. Yeah, those online, please feel free to put it in the chat. We'll look at them later, but we'll start here in the room with Kevin.
So I'll ask a question about the stuff towards the end. So you kind of prefaced it with, there's been this work that has suggested that there's a potential change in the environments, but that doesn't necessarily say anything about the storm scale. But I'm curious if you've done the calculations for these perturbations that you're adding over your area. Do those also predict? I mean, is there a connection potentially between the weakening that you're seeing in precip and those environmental variables for that specific perturbation that you're applying?
That we did not do, actually. Yeah, so that would be one thing. And so a lot of the work looks at these Cape shear balances. We wanted to take a step back and look at just fundamental state variables, basically. And so that comparison might be a little bit trickier. What we can do, and what we are actually doing, are looking at what is the Cape magnitude across the domain in the simulation, or what is the 0 to 6 kilometer wind shear in that. And so that's actually calculations that are going on right now. And then we can take that and compare it to what some of the projected differences are. That's the best way I can think of, at least on a case-by-case basis. But if you have any ideas,
Well, no, yeah, I think that would be the right way out, because
Okay.
I'm just thinking about trying to connect,
yeah,
right? Because it might provide better evidence that some of these large scale things are reasonable, or it
Yeah.
might suggest that they're way off, right?
Yeah.
And that's like the open question.
yeah.
I guess a really quick question. So when you run these runs, so you're initializing with her, but for the perturbed ones, do you use the same exact initial conditions, or do you perturb the initial condition?
So we take the HER and we perturb it. So we add those vertical profiles, like the climate perturbations, that gets added to the HER.
Okay.
And then we run the model.
As well as the boundary condition.
Yes,
Yeah.
and so everything else is the same. And so we just add, everything else is the same. We just add temperature perturbation or specific humidity. So surface layer is the same. Everything is the same. So we don't touch any of that stuff. And so we're really just addressing the atmospheric variables for that.
Yeah, Michael.
Going back to the precipitation that's out ahead of the squall lines.
Yeah.
Talk about the different mechanisms. Some of those are fairly complex and not, at least to me, not obvious. Operationally, do any cams pick up on these mechanisms? Is this at all forecastable to get those the precipitation pouring out ahead of the lines? I mean, is this just kind of a disaster forecasting wise?
Maybe. So I haven't gone through and looked through, though that might be something that we're considering doing, basically starting now with the folks at oh my goodness, at SBC, but the Orno forecast people. We're considering digging into that and seeing if we see any of these processes in the Great Lakes areas and how well the predictability is up there. And then hopefully we'll see, some of these types of evolutions, but we have not gone through and compared. I mean, obviously we've seen observations, but I've not gone through the cams and specifically looked and seen how many times it would be a bust. But yeah, look at all the small scale details that you have to get right in a model, which they're not going to get that right.
I
So
would think the collision, I would think, is something that maybe that they could pick up on, but
yeah,
the you're talking about the gravity waves and that type of thing. It's just,
Yeah.
it's complex and it seems, well, I don't know, I wouldn't say hopeless, but boy, that's a lot to ask.
So, the models do get gravity waves. I mean, it even has problems though with the sea breezes too, right? They don't necessarily get the sea breezes right either, which is then going to impact that collision. And so,
You gotta get a lot right.
yeah,
What are the scale of this gravity waves? They're small.
they're small.
Yeah.
Yeah.
So it's operational, boy, that's.
Yeah, you're not going to
That's-
resolve
I
that.
was just following,
Yeah.
I was curious, I mean, you showed that example where there was that, convection out ahead with the sea breeze, but how much of that was gravity wave versus CI impacts? It wasn't clear. Have you been able to separate the relative contributions of both?
For the observed cases or?
It was the idealized. I think you showed that field of convection out ahead of the squall line.
Yes.
And
Oh, yeah, yeah.
and I assume that's and you said it was, some of that may be gravity wave initiated, I think, and then you showed
Yeah.
how the evaporation and CI may be influenced. And so I wasn't sure. I'm only mentioning that because some of those might be better operationally to get than others. I think the gravity waves are going to be a real bear.
Yeah,
If it's evaporation and some kind of thing, maybe there's a fighting chance with the microphysics scheme or something doing it, but who knows? But I wasn't sure if there was it was this one, yeah, right.
yeah,
Where I think it was just discrete, but these cells out ahead, which the question is, these are being triggered
Yeah.
and through the gravity waves
Yeah.
primarily,
Yeah.
and then
Yeah.
okay, so.
and so, but it is in a storm modified environment, and so, I don't know. So the combination of the lower tropospheric from the sea breeze and the mid tropospheric from the storm, I mean, that definitely gets you your vertical ascent. And if there's any instability, I'm assuming that's fine, but it was in a storm modified environment too, with enhanced instability. And so,
You need that extra CI for this to happen. I guess that's
at
my
least in
question.
this particular environment, yeah, which was kind of surprising. So,
Well, that is scary.
yeah.
Okay, Pavlos, you had your hand up first.
Okay, excellent presentation, very nice. I have to say, I don't think you had a slide with observations, and I wonder if the case is that there's no room for error in the model interpretation, fits perfectly reality, or the observations are lacking. If they are lacking, how is that possible? We know where the coastline is, we know where the mountains are. Where's the calibration? How you talk about 10-15 meters ascent at the front, the convergence, and not have a snapshot of that happening?
He does this to me. Just say the models are perfect. We'll go home.
Okay. No, the models are not perfect, right? And I guess, so, I guess that's the question, like, why are we not using observations to look at this right now? Is that kind of what you're getting at?
I mean, the model interpretation was perfect, and all everything presented well explained and very informative. Should I assume that the model does perfectly representing the true atmosphere? And if not, give us test or calibrate this model actually is proper to handle these processes. And we talk about the MBL depth. How do we know it's 750 or 1.5?
Yeah.
Anybody got that measurements of that?
No. Right, well, they do, but not in real time for like a predictability standpoint. And so we do have measurements of sea breeze depth, and that's basically what we use to bound the range. But yeah, this, obviously we're in an idealized world. The physics processes, the models get right, but we're also oversimplifying the problem. And so in reality, there's a lot of other things going on that we're not including here just so we can diagnose the processes. So I think these will be in reality. It would be great to get measurements, and we've tried hard for years and haven't gotten money yet. But there's also going to be other complications. And so I feel like starting here is good because then you sort of know what to look for in the more complicated scenario and observations. And so we did perform a case study, wasn't near the coast, but it was with the mountains. And we saw processes, and this was actually, it was related to the triggering of a bore and the generation of a regeneration of an MCS. And so that's actually stuff that we see in these idealized simulations. And we did see that in observations. And so I think there really is a connection in the physics between what we see in these idealized simulations and reality, but reality is just so complex because it's not just that. So, but yeah, I really am trying hard to get more observations.
Yeah, King.
Yes, Kelly, hi. Good
Hi.
to see you back.
Yeah, you too.
Very interesting talk. That reminds me of one event which flooded this whole building and damaged all the compartments here. Yeah, so that's back several years ago, in summertime.
Yeah.
Also in free time. So it reminds me, your experience with the diurnal cycle signal plays some role in these interactions of this.
Yeah.
line.
Yeah, and so we don't have it here. We only included it obviously for our Seabreeze development, which I didn't mention, but we had to for the, obviously to generate the surface fluxes and stuff. But yeah, and so that'll definitely modulate, well, a number of things. One, simplified is just the instability that the storm is able to use. Two, the boundary layer. And when you start changing the boundary layer, then you can shift from something that's surface based to potentially elevated, and then you can start getting, other ways of kind of moving your storm forward, like bore processes and things like that. And so the diurnal cycle will definitely play a role in this for sure.
Yeah, a little specific to your sensible heat distributions along the slope.
Yeah.
Are they all the same or just decreasing some in some way we go up the slope and all the way to the top?
And so it's actually maximized at the top, decreases down the slope, and then also all of that is diurnally varying as well. And so we started at 8 a.m. And so that graph that I showed was actually at noon, and so we peaked out the H naught basically at that time. But then it would decrease through time, the magnitude. So we'd still have a continued pumping of heat. It would just less heat as we go past noon. So yeah.
Cool. Any others? Yeah, well, go for it.
Yeah. So for the first part, the mountain and the sea breeze both would affect the depth of the cold pole.
Yeah.
And also the low level wind relative to the propagating core line.
Yeah.
Have you tried to look into the RKW theory, whether that works in your cases?
So you can, it's challenging. So we're finding it, or at least I find it a lot easier to think about things in terms of pressure perturbations, because that basically just drives the airflow, right? If you see a pressure perturbation that's high, see a low, what direction things are going. And when we plot that and we plot parcel trajectories, things work out beautifully. RKW always gets challenging because you have to figure out, what size box do you want? And when you're on a slope, right, that gets a little bit tricky. You're thinking about a flux argument instead, right? So it's a vorticity flux argument rather than a kind of a movement of air argument, right? And so that's kind of the crux of the whole thing. Also, it only describes lift in the lowest part. So we're only thinking about lift across the cold pool. It kind of forgets about everything above that. And so it basically implies, whatever ascent or your, C over delta U relationship you have near the surface is going to apply, all the way up. And that's not necessarily true either. And so we've gravitated away from that and just kind of thought about it from a fundamental physics standpoint. And it's just made it so much easier in these complex areas. So we don't have to worry about, what are the bounds, what's the height, what's the length of these things, because you have to figure out how long you want your box, and vorticity doesn't necessarily move air, it's the pressure perturbations. And so we've definitely tended towards this. And I'm kind of on a crusade to get people to think about pressure perturbations because it's just easier to think about airflow that way. So
We had a student, Barat's not here, but Diego, he had a paper, that his PhD on looking at pressure perturbations with Squall lines.
Yeah.
And because of RKW, and that was years ago.
Yeah.
I'm sure there's a lot of work since.
Yeah.
I was, my only general question, I mean, a lot of internal stuff going on, thermodynamics and so forth, but yeah, what about sensitivity changes in shear and the background? It does, are your results strongly sensitive if you change the shear by 5 meters per second, like from those two basic soundings? I mean, you know what I mean, where you have the mid-Atlantic sounding, the other, I mean, so you have a certain shear. So that's the other controlling thing, right?
Yeah. And so primarily that would be, how much is that actually going to change your intensity of the storm? For these, it doesn't. But that's not to say for other soundings, it's not going to be as important. And so, because we have, we don't have amazing cape, but we have some decent cape in these profiles. And so, modifications to the wind shear are sort of less impactful. But if you start changing that in a low cape environment, then you have to worry about things like entrainment and all that kind of stuff. And so for these very idealized scenarios, we didn't, but that is something to consider for sure. Definitely in observations, and then, for other profiles that we're not using. So, yeah.
We don't need more variability.
Yeah.
Okay, I don't know if they meant we could check quickly on chat, just to see. I don't want to ignore it completely, but maybe it's. But while Kelly's doing that, yeah, there's going to be lunch afterwards, and then hopefully the students can meet with her for a while. Is there anything? No.
Yep.
Okay, good. Well, let's thank Kelly again for a great seminar.